Hi everyone. So today I'm going to talk about machine learning in epidemiological models. For this particular discussion, I'm going to use this one reference that is going to be the primary reference for this particular discussion. And this is a paper by Qifeng Bai from American Journal of Epidemiology in 2019. So let's start with our epidemiological models. We generally use an outcome, we generally use an exposure variable, and we generally have a number of confounder variables, or we can have an outcome and we have a bunch of predictors that are predicting our outcome, right? Say, for example, one example can be cardiovascular disease can be our outcome, and we have smoking, age, diet, obesity, cholesterol level, family history of heart disease, everything as a predictor of that cardiovascular disease. Where we make distinction about type of models is that whether we are focusing on only predicting the health outcomes, say for example the cardiovascular event, is that the only focus of our modeling, or we are really interested in the relationship between the cardiovascular disease and the smoking, and everything else is basically confounding factors that we are adjusting to get a good sense of the adjusted relationship between cardiovascular disease and smoking, right? So in the first case, when we are building our predictive model, then basically smoking, age, diet, obesity, cholesterol level, family history of heart disease, all of these are predicting the cardiovascular disease status, right? But in the second case, what we are doing, we are trying to find the association between the cardiovascular disease and smoking, and everything else that can be a confounder that can confound the relationship, we are adjusting for those, right? So in terms of epidemiological model, these are the two basic or main type of models that we generally see. All right, so historically what has been happening is that majority of the epidemiological models were fitted by some sort of parametric regression. Say for example, in terms of fitting medical datasets or the models, logistic regression is very popular, right? And this is okay in a scenario where we have a limited number of observations and limited number of variables, and we can really think very carefully about the model as well as the data and how the data generating process is working, how the disease is working, how the people participating in that study are behaving, and all of this gives us a sense of how to build the model. Especially the epidemiologists are very good at identifying how the whole causal process is going on, and then they try to use those understanding in the modeling. But as more and more datasets are becoming available in this big data era, because nowadays governments are collecting a huge number of information, the insurance company is collecting a huge number of information from various pharmacies, and all of these pharmacies are linked together. There is a common database, and they are collecting huge number of variables and observations. And as a consequence, what is happening is that nowadays when a health researcher gets access to the dataset, there is enormous amount of data, and trying to sort out some of the most important variables from that dataset is actually very hard, even for an epidemiologist with good subject area knowledge. And that's where this basic statistical or conventional statistical models such as these parametric or logistic models are suffering, and we need some data adaptive tools that can guide the analyst in making the process a bit semi-automated, so that the analyst can give some input of what is necessary and important, and from the big data we can also try to get some idea of which variables are probably giving us more signals about which relationships and things like that. So it can be a combined approach to tackle a given problem. Alright, so as you can understand, these machine learning methods have been out there for a very long time, and these machine learning methods, especially some of these machine learning methods, are very well known in terms of dealing with big data, right? So these machine learning methods can be potentially useful in analyzing some of the epidemiological data sets that we have right now. But the issue is that when an epidemiologist is trying to learn more about the machine learning methods, it is not easy, in the sense that machine learning method is a field on its own, and depending on who you ask, they might give you very different answer about what is actually a machine learning method. Say for example, do you consider logistic regression or stepwise method as a machine learning method? When you use a AIC criterion to choose the model, is that a machine learning method? Or when you are using a lasso method that uses some sort of cross validation to select the parameters associated with lasso, is that a machine learning method, right? So there are many schools of thoughts that combine in the machine learning literature, but to give a very brief oversimplified definition of machine learning, if in the Kifang-Bai's paper, the way they have defined it, that these are the general characteristics of machine learning, is that they prioritizes the predictive accuracy, and also they're a bit less focused on the inference and hypothesis testing compared to conventional statistics. And these machine learning methods are capable in handling big data. And by big data, what you mean? I mean, different people answers it differently. Some people says that if you have a large number of observations, large number of participants, then you can have a big data. Or if you have a large number of covariates, so you are now talking about the data columns, then that can be a big data as well. So technically both of these are true, and certainly in this day and age it can certainly be possible that especially in the electronic healthcare datasets you might have large number of patients, say for example all of the patients from British Columbia, and large number of covariates from each of these patients. So one of the things that jumps out from this oversimplified definition to me is that they are only talking about predictive models and giving more priority to the predictive model. Does it mean that machine learning methods are not at all useful for building causal models? So there are some literature in this, and at the end of this discussion we will see some examples where these predictive models or machine learning models are also useful in developing some of the causal models. Alright, so before we move on to more generalized description of machine learning algorithms and techniques, let us try to get familiar with some of the terminologies that we as epidemiologists know very well, but in the machine learning literature maybe they are explained or termed in a different way. So one example is that the outcome variable, so for example in our case we had cardiovascular event as our outcome variable. We call them dependent variable, predicted variable, but in the machine learning literature, you will see those are commonly known as output. And for the cardiovascular disease status, there could be two different status. One is that person has cardiovascular, or that person do not have any cardiovascular event. And these are the possible values of the outcome, right? And in machine learning literature, these possible values are known as label. The cardiovascular event can be rare. That means that there would be less cardiovascular diseased patient versus there will be a lot of patients who are not associated with cardiovascular event. And in that case, our outcome will be imbalanced because they are not really 50-50% overall. If you have a outcome group that is with highest frequency, we generally call them majority class. If you have an outcome group that is associated with lowest frequency, we generally call them minority class. In terms of the independent variables, such as the age, diet, obesity, cholesterol level, family history of heart disease, and things like that, we generally call them independent variable, explanatory variable, or predictor variable. But in the machine learning literature, they are known as attribute, very commonly known as feature, predictor, or field. In epidemiology, we are most particularly in the causal models, we have a primary predictor of interest, right? Or primary variable of or exposure of interest. And in the machine learning term, we generally call them input. And remember, when we are talking about the large number of covariates, we are generally talking about large dimensions. That means the number of covariates are known as dimensions in the machine learning literature. The other examples are what we call as model. Machine learning literature calls them classifier or estimator. The model fitting algorithms are known as learners in the machine learning literature. Also, the domain is known as the range of possible values, and for the type of error measure that we use, such as the mean squared error and things like that, we usually call them loss function. Alright, so now that we are familiar with some of the machine learning terminologies, let us talk about some of the type of machine learning algorithms that we can have. The first type is supervised learning. And in the supervised learning, we generally know the labels of our outcome. So in this type of modeling, what will happen is that we will know what are the possible values or labels of the outcome. Whether a person has cardiovascular event or not is the possible labels or values of our outcome. Say, for example, let us consider a situation where we are really interested to find out the risk of cardiovascular event of some person who got admitted in the St. Paul hospital this year. So to build the model, what we try to do is we try to collect some data, say for example from last year, where we collect some of the predictor variables, say for example age, obesity levels, cholesterol level, and we also collect the data about the outcome and the labels, whether they had cardiovascular event or not. Based on this predictor and the outcome, we try to build the model. How do we build the model? One example can be by using a logistic model or a lasso model, or some sort of regression and classification tree model that we will talk a bit later. Once the model is built, we fit the model, and then we use that fit to get prediction from the new subjects that we recruited in this year, maybe 2020. And then based on this new data set and the model that we have already built, we can get the risk of cardiovascular event for each of the persons that were recruited this year. So in this example, as you can understand, this Y variable we already knew in the model building process who had cardiovascular event and not, and based on that we were able to build the model. The other type of model can be unsupervised learning, where we do not really know the labels of the outcome. So here is an example that we borrowed from this particular book, where you can see based on the clustering in the dataset, the algorithm will try to identify that these points may belong to one group, these points may belong to another group, and these blue points may belong to another group. So it will subset the data or subgroup the data based on some sort of clustering, and these clustering algorithms are generally within the unsupervised learning category. There is a third category which is known as the semi-supervised learning, and it is some sort of compromise between the supervised learning and unsupervised learning. And the way it works is that you take a subset of the data and you label them. Say for example, in a MRI data, you can try to look at the MRI image and you can try to identify which are coming from a healthy tissue and which of the pixels are coming from non-healthy tissues, and then based on that you can try to label them as healthy and unhealthy, but you do it for a subset of the data only, and then you give much larger amount of information, and then based on the training data that you have given the labels, you can try to build the labels for rest of the data sets. And as I have already explained in my example, that in the medical imaging these type of algorithms are very popular. Alright, so in terms of the supervised learning, I want to focus a bit more on the supervised learning because in the epidemiological models, these supervised learnings are used extensively. So in this supervised learning, we can have classification and regression. The classification is mostly about the prediction of categorical outcome. It could be even binary. It could be three labels in the outcome, 4 labels in the outcome. And our logistic regression could be one way to deal with these categorical outcomes or the binary outcomes. For the situation when we are predicting a continuous outcome, such as the BMI in a continuous level or systolic blood pressure in a continuous level, and then we can try to predict using a either linear regression or any other regression type of methods that can handle continuous outcomes. Right, there are some other classifications. I'm not going to go into too much detail about them, but generally speaking, when you first build a joint probability and then try to decompose this as a joint probability divided by the marginal probability to get the conditional probability, that kind of models are known as generative models. But when we generally try to build the conditional probability or obtain the conditional probability from a model, that is generally the discriminative model, and usually the epidemiologists use this kind of model more, where they simply model one variable given another variable, where this y variable can be the outcome variable and the x variables could be the inputs from the predictor list. And there is another classification known as the reinforcement learning, and these are a bit much more complicated to explain, but generally speaking these are self-adaptive and they learn gradually and iteratively to improve the performance. Alright, so let us talk about some of the popular machine learning algorithms. Especially I'm going to talk only about the supervised learning algorithms that we generally use in the epidemiologic literature widely. The first kind of algorithm is the decision tree. The second kind of algorithm is the shrinkage methods. Especially these kind of methods are very useful in identifying important variables. And the third kind of algorithms are known as ensemble methods that generally combines or harnesses the power of many different algorithms. So in terms of the decision trees, it is a decision support tool that has a flow-like structure, and these are commonly known as the classification and regression trees, particularly because they can deal with categorical outcome as well as continuous outcomes. Depending on what type of outcome you have, you can either choose to go with classification or regression within this decision tree. And part of the appeal of this decision tree is that these are very easy to understand and they are very flexible. So there is no direct parametric form, and as a result it can be very flexible to incorporate some of the nonlinear effects automatically. So in a logistic regression scenario, you can imagine that an analyst will have to figure out which interaction to include, which higher order term to include, and for an analyst it can be very challenging in a scenario where he does not have enough subject area background to have a good sense of which interaction might be useful in a given context, versus in a decision tree type of modeling, an analyst do not need to specify those interaction term or polynomial term. The decision tree will be flexible enough to identify them. But the downside of this decision tree is that these are unstable to some extent, and there is some subject to overfitting, and often they are subject to high variability. So one very crude example that I took from this towardsdatascience.com, where they have some brief explanation of what is a decision tree, and this gives you a very crude understanding of what it may look like. So when you are looking outside to just get a sense of whether you have a rainy day, overcast day, or a sunny day, that can give you some tools to make a decision about whether you are going to play golf or not in that particular day. So say for example, if you have a rainy day, you might choose not to play golf. If you have a overcast day, you might play golf. If you have a sunny day, then given that it is a very windy day, you might consider not playing the golf anymore. But if it is not a windy day, you might decide to play golf. So as you can see, there are some layers of variables or observations that are helping you to make your decision. Alright, so let us get familiar with some of the terminologies that we use in our decision trees, and this is one example that I have borrowed from this particular paper, where they were trying to give an example from medicine. The first variable in the language of the decision tree, these are called nodes, and since this is the first variable, we call them root node. And this root node is then splitted into other nodes based on some splitting rule, and these splits are generally selected to minimize some of the measures of node impurity. By node impurity, they generally mean the diversity of classes, or it could be based on variance minimization, and that will lead us to partition of these additional nodes. And these additional nodes can be known as daughter nodes or branches or subnodes, and at the end of the decision you will see this is the end of the decision, and that node is known as the terminal node or the leaf. As I have explained in the previous slide, is that often when we are splitting too much, then after a while it can feel like overfitting, and then we might want to make the decision of reducing the size of the tree. So we would prune some of the leaves, and then we will come back to some of the prior nodes to keep the stability of our decisions. So since these decision trees are very easy to understand and they have quite interesting interpretations for the epidemiologies, so in the medical literature you will see some applications of these decision trees. Alright, so let's move on to the next machine learning algorithm, and this is known as the shrinkage method, and essentially these methods are extensions of the general regression that we do. And in a general regression, what we do is we minimize the residual sum of square. Remember, the residual sum of square is basically the difference between the observed y value versus the fitted y value based on a particular model that we have already built from the data. And we simply take the square of that and sum them, and this is the residual sum of squares. And in that residual sum of squares there are no penalty term, and in particular when we are dealing with high dimensional data. Remember what is high dimensional data? That means we have lots of covariates in our analysis. In that case, when we are trying to build a prediction model, generally there might be some instability due to this overfitting problem, and many other different issues can happen. And to get a more stable result, one of the techniques that are proposed is this shrinkage method, where you are simply modifying the error function, where you are forcing all of the beta coefficient to be non-zero, right? And in that case what will happen is that you are simply adding a lambda multiplied by sum of all the beta j square term in your residual sum of square. And these two terms require some explanation. So this second term that you are seeing, that sum of beta j square, is known as the ridge penalty or the L2 norm, and this first term that you are seeing is the lambda, or this is the regularization parameter that can be determined using a technique known as cross validation. And using the cross validation technique you can minimize this error. And this lambda is basically the the parameter that is controlling the strength of the L2 norm penalty. So this is one way to bring some stability in your estimate. The other kind of shrinkage method is the lasso method, where instead of the beta j square you are just assigning the absolute value of the beta coefficients, and these coefficients are known as the L1 norm. The sum of beta j absolute terms are known as the L1 norm. And one of the advantages of this particular penalty term, and by penalty term I mean lambda and beta both in this particular situation, where these are very helpful in omitting some of the variables that may be highly collinear with some of the other variables in this covariate list. And because of this multicollinearity, the model can be very unstable, and by deleting some of the variables or a subset of the variables from the regression, these shrinkage methods are trying to bring some stability in the analysis. And basically by addressing collinearity, we are also reducing to the variables that are mostly important and giving somewhat independent information about the outcome. Right, so the previous method that we were discussing in our previous slide is known as the Ridge method, where we use the L2 norm, and the new method we just discussed is the lasso method, which is basically using the L1 norm. Right, so as you can see, the only difference between these two is the penalty term that we are adding. In the first one we added the square term, in the second we are adding the absolute term. But often what happens is that in the ridge regression we cannot really use that regression as a variable selection method, because it is forcing all of the variables to be in the model, whereas in the lasso model we are deleting a lot of variables that has some correlated variables in the model. But often it can happen that if you have a group of variables, lasso will try to pick just one of them and it will delete the rest of the members from that group. By group I mean the variables that are collinear with each other. But often that can be viewed as a extreme measure, and as a result of deleting a number of variables it can be quite unstable. So as a compromise between the lasso method and the ridge method, there is another method known as the elastic net method that actually combines the ridge and lasso penalty terms. So it is using the L2 norm as well as the L1 norm, and it is using another parameter known as the alpha parameter, which is known as the mixing parameter. So if you have a error function where you have this residual sum of square, the L2 norm and the L1 norm, the only thing you need to do is to change the mixing parameter to either get to the ridge regression or the lasso regression or somewhere in the middle. So if you put this alpha equal to 1, this will essentially turn into a L1 norm, and this term will become 0, and this will convert into a lasso penalty. And if you put alpha equal to 0, that means that it will only have this L2 norm, but this L1 norm will vanish, and this will again turn into a ridge regression. So you can imagine putting this alpha values somewhere between 0 and 1. Say for example we are putting a value of 0.2, and that will give some strengths that are coming from the L2 norm and some strengths coming from the L1 norm. So what will happen in that case is that we will still delete a number of variables based on high collinearity, but we will delete less number of values compared to a lasso penalty, right? So this is kind of a compromise between the ridge regression and the lasso regression, and we are just trying to sort out our alpha values to do that. Alright, so In this particular scenario, what we are doing is that we are showing all of the equations that will probably give you a better understanding of all of these methods and comparison. So this is a regression method without any penalty term. This is a ridge regression where we are forcing all of the coefficients to be non-zero, and we are using our L2 norm, and in here we are using our L1 norm, and this is essentially the lasso method, and this elastic net method is basically a compromise between these two. And how do I get these lambda values? Essentially we are doing some sort of cross validation to get these lambda values. Alright, one general comment that I want to make is that in the epidemiologic literature there has been suggestion of using these lasso methods to find out the most important variables in an analysis, and often these methods were even suggested to be useful in finding confounders. But if you are doing a model selection based on a shrinkage method and then you are putting them in a non-shrinkage method, by that I mean if you have 10 variables in total and then using shrinkage method you come down to 5 methods. Say for example by using lasso or elastic net method you come down to 5 variables. Then if you are just using those 5 variables to run your general regression without any shrinkage, then that method is not really the best method. In general, whenever we are trying to use some of these variable selection machine learning methods to select confounders or find a parsimonious model for our analysis, then we need to be careful about making inference later on, because that has some additional implications. Alright, so the last method that I want to briefly mention is the ensemble method, and in the ensemble method we are essentially using multiple methods to improve our predictive performance compared to one single method. By that what I mean is that when we were using the shrinkage method we were only using, say for example, lasso method. When we were using the tree based method, that is only one method. But in the ensemble method what we can do is we can try to get our prediction based on multiple of these methods, and then we can aggregate our prediction. And in the epidemiologic literature there has been some studies where these ensemble methods were shown to be very effective in finding good predictions. Alright, so there are a couple of popular ensemble methods that are available in the literature, and there are two different main types of ensemble method. The first type is when you are using same model but different versions of the data or different samples of the same data, and the second type that we will talk about a bit later, where we are essentially using different models on the same data. Right, so let us talk about this first type first, when we are training the same model but on different samples of the same data. Some popular examples can be bagging method, boosting method, and random forest method. So in the bagging or the bootstrap aggregation method, what we try to do is we try to first get some independent bootstrap sample. Say for example we can have say 1000 training sets, and then we apply the cart method or the classification and regression tree method that are usually known to be very unstable, right? And then we average the resulting predictions, and as a result what will happen is that the instability or the high variability of the predictions will get averaged out, and that is one advantage of this bagging method, is that will reduce the variance of the cart method when we are doing it using the bootstrap. The second method is known as the boosting method, where instead of the independent bootstrap sample, we are sequentially updating the bootstrap samples based on some sort of weights, based on what we have learned in the previous step. In the random forest method, which is going to be an improvement over the bagging method, where we are tweaking our algorithm in such a way that can deal with some correlation issues. One of the very useful application of this bagging approach is that it can help you identify the variables that are important in predicting the outcome, and you can get a plot like this by the importance of the variable. But as these plot statistics are coming from a lot of bootstrap estimates, so it is very hard to interpret. But in a general sense, in the epidemiologic literature, many have used this plot to justify which is the important variable in the prediction process. And also from the random forest and boosting, you can get similar type of variable importance measures to draw this kind of plots. The second type of ensemble methods are known as the type 2, or the in a situation where you are essentially using different models, but you are keeping the data same. You are not subsetting the data, or you are not really replicating the data in any way. There are two examples. One is Bayesian model averaging that can use a wide range of learners on the same dataset, and then it basically averages out the results. The second type of learner here is known as the super learner, that has a lot of application, especially in the causal inference literature, where what you are doing essentially is that you are collecting a lot of candidate learners. So for example, you can include some parametric learners, you can include some sort of non-parametric learners, and then by using these candidate learners in the training data, you can make the prediction on the test data, and the final prediction that you get out of these super learners are basically some sort of weighted versions of all of the predictions that you get from all of these models. So you can imagine when you are using the parametric model, you can probably have less variance, but you are dependent on the model specifications. So if your model specification is incorrect, then your predictions are probably not as good. But when you are also using some sort of non-parametric methods, where you are not really forced to specify your model specification directly in terms of the interaction and polynomial terms, then it can automatically identify those patterns, and when it will give you the prediction, it will be less problematic in terms of the model specification. But then again, when you are using non-parametric methods, sometimes you might get less efficient results than the parametric regressions. And in that sense, there is a trade-off when you are using all of these kind of candidate learners to build your super learner prediction. And it was shown in the literature that this kind of learners can be very helpful in real life situations when it is very hard for an analyst to figure out the model specification properly. And then this kind of learners can be very helpful in giving you a more realistic version of the prediction, rather than just a parametric or just a non-parametric method. Alright, so in the Kifang Bai's paper, you will see in the web appendix they have given you some plots that will probably give you some more understanding of how these classifications are different from each other. So one of the things I have mentioned earlier in the discussion is that the definition of machine learning revolves around prediction more. But is there any space of these machine learning methods when we are trying to deal with the causal inference? So in general, in causal inference, there is a method known as propensity score modeling that is widely used, and this type of propensity score models are very popular. To explain you this propensity score model in very brief, these are done in two separate steps. For example, let us talk about this cardiovascular disease versus the smoking example. So in here, cardiovascular event is going to be the outcome and smoking is going to be the exposure, right? So first we try to do the exposure modeling. So that means we are modeling our smoking as outcome with all of the features or covariates that we have, and that will give us some predicted value of what is the probability of being a smoker given all of the other features or covariates, and those probabilities are known as the propensity scores. And in this particular step, when we are building our exposure modeling, in the literature of the propensity score, they suggest us to use rich model. That means you can use interaction term, polynomial terms to build a better prediction model so that you can predict your smoking status better. But later on we have some other considerations such as assessing balance and things like that. But in this exposure modeling step, what we are essentially doing, we are building a prediction model for the smoking. So in this particular step, machine learning methods can be very useful to develop our propensity score model. And the reason is obvious in the sense that when you are using a logistic regression model to build your propensity score model or the exposure modeling, then you have to manually input which is your interaction, which is your nonlinear terms or polynomial terms that you are trying to add. But if you are simply using some CART method or some of the Ensemble method version of the CART, such as bagging, boosting, then you can essentially build a better prediction model for the smoking, and you can get propensity scores from those models. And this is the first step. The exposure modeling is the first step, and once we are happy with our exposure modeling step, so in that second stage we can do the outcome modeling, and in the outcome modeling stage we can try to find the association between the cardiovascular event and smoking after dealing with the propensity score, either as a matching variable or as a weighting variable or as a covariate in that regression. So the main message I want to convey from this particular slide is that even though in causal modeling prediction is not the main goal, but there are some scopes of using some of these useful machine learning tools when we are particularly doing a step that requires good prediction, right? And these propensity score modelings, when we are doing it in a small scale data set, those are very easy to check. But when we are doing it using a very big data set, then some of these parametric models such as logistic models are extremely inadequate. So some of the machine learning methods such as the super learners or some of the high dimensional methods such as the shrinkage methods can be very useful in building better prediction models when we are dealing with high dimensional data. Right. So other than these high dimensional propensity scores, there are more scopes of using these machine learning methods, such as these causal trees that are recently been introduced in the machine learning as well as in the causal inference literature that have some usefulness. Also, the causal discovery is a very old field, relatively old field in the machine learning literature, where you can try to predict the causal diagram based on the associations that you can see in the dataset. And those causal diagrams can be very useful in the causal inference literature as well. There are some additional methods that can use that, such as the targeted maximum likelihood estimation, that generally uses the superlearner methods, typically when they are trying to build their model in a particular step. So we are at the very end of our talk, but some of the things that I have already discussed during this talk, I just want to summarize in this particular slide, is that epidemiological data sets are getting large and large every day, and to cope up with the large amount of data, we need to also come up with models that can deal with those kind of large amount of data. And we also need to think about modelings and the assumptions that we are putting when we're building our models. And machine learning methods in some way can be very helpful to weaken some of the strong assumptions that we make in building our statistical models. Particularly when we have large amount of information, some of the machine learning methods such as lasso can be very useful in dimension reduction. Other kind of data set we did not really talk about during this talk was the gene expression data, where you can have many covariates compared to the observations, and then these data reduction techniques can be very useful. In the current context of COVID, for forecasting infectious disease, you will see a lot of publication going on around the prediction models built around COVID-19. In the high dimensional context, when you are building causal models such as the propensity score models, even then these machine learning methods have a role to play. And obviously, if you are trying to build a prognostic model or risk score model, then some of these machine learning methods can be very useful, especially some of these ensemble learner methods may have some good ability to deal with this building risk scores. Other type of datasets such as the geospatial datasets or the text mining, that can be also relevant when we are doing the epidemiological studies. And we are actively working in the field of machine learning and in the field of epidemiology to try to find out innovative ways to combine both of these disciplines together to make better predictions, to make better causal inference. So hopefully this talk will give you some explanations of how we are trying to move forward. So of course this is a very introductory talk of machine learning modeling in the epidemiological data context, but if you are interested to learn more about machine learning and statistical learning methods, here is a very interesting text that can be useful for you. And I thank you all for listening.